Hello, everyone, and welcome to today's live broadcast on Enrich Technology, a novel approach for isolating compounds that are difficult to purify. I'm Shannon Stoltz for LCGC, and I'll be your moderator for today's event. We're pleased to bring you this webcast presented by LCGC and sponsored by YMC. YMC empowers scientists and engineers by providing a full spectrum of liquid chromatography solutions, from resins and columns to the advanced Quantachrome cube and twin multi-column chromatography systems. YMC's mission is to help solve the toughest separation challenges for partners in the pharmaceutical, biopharmaceutical, and nutraceutical industries. To address the significant bottleneck of isolating low abundance or difficult to purify compounds, the YMC Chromacon team developed the Quantachrome platform. These systems, from the lab scale cube to the process scale twin units, enable novel continuous processes like Enrich. This technology automates the enrichment and isolation of target compounds, delivering high purity material in a fraction of the time required by traditional methods. So it's going to be a very exciting presentation, but before we get started, we do have a few quick announcements. First, this webcast is designed to be interactive, so we encourage you to ask questions throughout the live event. You can submit your questions by typing them in the Q&A box, which can be found at the bottom of the video player. You can enlarge the slide window by clicking on the small icon in the bottom right corner of the media player, and keep in mind, please, that the slides will advance automatically throughout today's event. Otherwise, if you have any technical problems either viewing or hearing this presentation, you can please click the !help widget in the top right of your presentation window. I'd now like to introduce today's speakers, Dr. Thomas Miller-Spate and Dr. Jay Preston. So a bit about our speakers. Dr. Miller-Spate is CEO and co-founder of Chromacon AG. He earned his PhD in continuous chromatography at ETH Zurich and is a patented inventor and author. Dr. Jay Preston is Director of Separation Sciences at YMC America, has years of experience focused on chromatography in the pharmaceutical industry, and he's worked for multiple pharmaceutical companies. With a doctorate in analytical chemistry from the University of Illinois, he's published numerous peer-reviewed articles, and he's given many presentations at national and international meetings. So thank you both so much for joining us today. We're very excited. Please get us started.
Welcome to my presentation about the Enrich technology, a novel approach for isolating difficult to purify compounds. My name is Thomas Müller-Spät. I'm the CEO of YMC Chromacon and one of the founders of the company. So Enrich is a technology that is used for isolating difficult to purify compounds. And after first introduction to our company, I'm going to introduce this technology, the process principle, case studies, and its key advantages. So YMC is a company offering stationary phases and columns, and also biopharmaceutical purification systems, as well as synthesis and purification services. So the technology I will present today is a process that can be operated on the continuous chromatography systems that our company is offering. These are called Quantachrome cube systems, and you can see them on the right-hand side of the slides. These are benchtop purification systems for automated continuous chromatography. So they are capable of running the Enrich process, and the main advantages of this process are the reduction of processing time when isolating impurity standards, the increase of purity of those standards to up to 95%, reduction of analytical samples, and operation with minimal manual handling, as well as savings in up concentration and secondary purification steps, which minimize then sample degradation. The applications of this Enrich technology are the isolation of the impurity standards for monoclonal antibody charge isoforms, peptide impurities from chemical synthesis, oligonucleotide impurities from chemical synthesis, and also mining and isolation of natural products with a therapeutic potential. So what does this technology solve? Which problem does this technology solve? So when we isolate minor compounds from complex mixtures using HPLC, we need a lot of material, and most importantly, we need a lot of time. So for example, if we do map charge variant isolation and we want to generate a certain amount of impurity, we need several hundreds of hours typically to get to a quantity of, for example, 10 milligrams. And also the purity of this isoform can be very low. Question is then, why does it take so long? Can't we just load more on our chromatography column and produce more? And you see the problem down here in these figures. The answer is no, because the main compound will overgrow the target compound as the load increases. So we see here our target compound, and the main compound is shown on the right. And you see as we increase the load, it overgrows the impurity and the target compound will not be pure. So the question then is, can't I just scale up my analytical column to load more? The answer there is yes, you can, but analytical resins are very, very expensive. And your HPLC, also your equipment may have flow rate constraints. So that can be an expensive option, but it may be also, there may be also equipment limitations that you prevent you from doing that. So the enrich process addresses this workflow of isolating impurities that is shown here on the left-hand side. So when you have a feed material, you load it onto the HPLC and you try to isolate your compound of interest. You have to take many fractions, which then have to go in the analytics. You're limited to a low load. And these fractions then you have to pool and redo this over and over again until you have produced enough material, the target amount. So in other words, the problems are here with this process. It takes ages and it produces many, many fractions to be analyzed. And there's a lot of manual handling of the fractions involved, and the impurities, they can actually degrade as time progresses. So the enrich process addresses this problem by automation, and also it uses internal concentration to generate the impurities faster and with higher concentration. So with this, you can reduce QC time up to 10-fold, and QC samples also up to 10-fold. The concentration you can achieve is 10-fold higher, and this avoids costly and lengthy concentration steps. This means overall, you can get your analytical standards faster and with less effort. There's no manual pooling and no repetitions of samples required as shown in the previous case. So how does enrich work? It consists of first of 3 steps. So the first step is the design step of the process, where you run a single column batch chromatogram on your Quantichrom cube system. You select a region of the chromatogram for the enrichment. Then you run the actual enrich process to get your impurities. You elute and fractionate them to have them recovered, and then you analyze them using HPLC. So you verify the impurities by analytical HPLC or UPLC. So each of those steps is only done once, and there are no manual repetitions. Looking at the process more in detail, the operation of enrich consists of 3 stages. The first one is an accumulation stage, where we enrich the impurities and we discard the undesired main compound. We load a new feed in every cycle. So enrich is a cyclic process that with every cycle accumulates the side compounds of interest. So this can be then repeated until enough of the desired compound has been accumulated. Then in the second stage, we deplete the main compound. So we stop the loading of new feed material, and we carry this out as a single switch to reduce the main compound. And then in the final step, we do a fractionated elution. So we elute the complete profile with a shallow gradient across both columns in series, and we do a very fine fractionation of the gradient. And then these samples have to be sent to the analytics, and we should have our target compound pure and with high concentration. So to explain this process a bit better, I have a short animation here. So here you can see the two columns that are used in the process. On the right-hand side, you can see a typical chromatographic profile containing our compounds of interest in the front and in the back that we want to isolate. So you can see we have our compounds of interest pure, but also we have overlapping fractions of the impurity compounds that we want to isolate and the product, the main compound. So here, main compound and strong impurities are overlapping in the back, and here we have the strong compounds pure in the end. So here we are interested in the strong and weakly adsorbing compounds. So we load those on the first, this feed mixture on the first column. The two columns are identical, by the way, and typically contain a semi-preparative material. In the case of monoclonal antibodies, this would be an ion exchange material, for example, with 10 micrometers or up to 30 micrometers. So we load the feed onto the first column, and then we start a linear gradient on the first column. And as soon as our compounds of interest elute from the first column, we interconnect the two columns and transfer these impurities to the second column from the first column. So you see this transfer happening here. And on the way to the second column, we do inline dilution to reabsorb these portion of the chromatogram on the second column. So the inline dilution is really there to lower the content of the modifier, which in case of ion exchange would be the salt concentration, to make this portion stay at the entrance of that second column and reabsorb there. Then looking back at the first column, the next portion of the chromatogram that's exiting this column is the product. The main compound, which we do not want to keep. So we discard this part of the chromatogram. And at the same time, we load new starting material on the second column, which then mixes with the fraction that has been recycled. Then looking back at the first column, now we have an overlapping portion coming off next and our strongly adsorbing compounds of interest. So again, those we want to keep inside the process. So we interconnect the two columns again and transfer this portion of the chromatogram by means of a linear gradient into the second column. We do inline dilution on its way there. So it reabsorbs at the entrance of the second column. So then you see we are at the initial stage again, just with the columns switched. And now the linear gradients started again, but this time on the right side, on the right column. And we transfer again the compounds of interest through the internal recycling to the other column. We make sure it reabsorbs by inline dilution. Then we take out the main compound from the second column, load new feed on the first column, transfer the overlapping portion and the strongly adsorbing compounds from the second column to the first column, do inline dilution to reabsorb them. And then we have completed basically one cycle of accumulation. We have had 2 injections of fresh feed, which means that we have reached some degree of accumulation already. And now we can continue this process to further enrich the front part of the chromatogram and the back part of the chromatogram while taking out the main compound to prevent the overgrowth of the compounds of interest. And now you can see already in this cartoon, the intensity of the color has changed, means that we have some enrichment. You see that here again as the strong compounds are recycled. So we have definitely increased the concentration of these compounds of interest. And ultimately, once we have repeated that, the required number of cycles, we can do the depletion stage, at which we do not feed new material, but we just remove the main compound, which you can see here as a red band. So we do one more recycling step, remove the main compound then, and do not inject new feed while this is happening on the other column. So this means the concentration of the main compound on the second column will be lowered. You can see that happening now, and we are just having the concentrated side compounds left on this column here on the right-hand side. So now we want to recover those side compounds. And to do this, we interconnect the two columns one more time. We run a linear gradient through both columns in series to maximize the resolution, and we collect the samples and forward them to the offline analytics. So you can see that now, the elution of the profile and the collection in the fraction collector, and then the samples are taken for the offline analytics. So what is very important in this process is that the enrich prevents the main compound from overgrowing the target compounds, right? So it accumulates the target compounds, and it removes the main compound due to the continuous removal. And this is something that cannot be achieved using a regular single column chromatography. So on the right-hand side, you can see chromatogram, an actual chromatogram from an enriched process where the side compounds are growing in the front and in the back of the main compound peak. And the main compound peak height is remaining the same from cycle to cycle. So this is more than 10 cycles here. But the main compound peak continues to have the same height in every cycle. So I mentioned initially how the process is designed. Just to repeat that again, we first have to load a batch chromatogram, and we load this batch chromatogram into a software tool that is called Enrich Wizard. So this Enrich Wizard helps design the enrich process. It's a part of the operating software of the Quantichrom Cube system. So we load that chromatogram, and using a drag and drop function, we select the regions of the chromatogram for accumulation in the front and in the back. Afterwards, on the next tab of this Enrich Wizard, we select the desired washing and cleaning protocol, how many column volumes of equilibration and cleaning are required. We can take that from our standard batch method. Afterwards, we enable a UV-based dynamic process control, and then we finalize the method by setting the number of cycles and the fractionation scheme. After we have saved this method, we can just execute it on the Quantichrom Cube system. On the following slides, I would like to show you a few case studies for peptides and oligo purifications. So the first one is for peptide purifications. This is taken from a scientific article in Journal of Chromatography that is called Enrichment and Purification of Peptide Impurities using Twin Column Continuous Chromatography. And this study demonstrates two strategies. First, the purification of multiple impurities of angiotensin II. And then a second example is a specific isolation of a critical impurity. So for this, the Quantichrom Cube 30 system was used, and we had synthetic angiotensin II, and the purification was run on YMC Triad Prep C18 columns of 10 micrometer. So for the solvents, a typical solvent system consisting of acetonitrile water and TFA was used. So as mentioned, this study is published in Journal of Chromatography A, and it's open access also. So for the first purification, where we want to isolate a broad range of impurities, we wanted to select the front and the back part of the chromatogram for the accumulation. And here you can see what that looks like. So the zoom in of the analytical chromatogram shows, for example, easy to isolate impurity in the front and the difficult to isolate impurity, which is eluting very closely to the main peak. So here we show how difficult the purification using single column chromatography is. So the moment we load more material on the column, and so increasing the load to 0.5 grams per liter and to larger loads, the moment we do that, we see that the main peak starts to overgrow the impurities. So here, for the different loads, we see on the lower right side a zoom of the chromatogram shown in C. And we see that the impurities that were previously easy to isolate, as shown in figure B, are now becoming much harder to isolate as we increase the load to 0.51 gram per liter, and they're actually not separated at all at a load of 2 grams per liter, which would be considered still a low load in preparative chromatography. Now, the difficult to isolate impurity that you can see is closely eluting in the figure B is not at all resolved on this preparative stationary phase. So it's somewhere below the main peak. We cannot see it at all. So these are the two cases that we want to address: isolation of easy to isolate impurities, and then second, we wanted to see what we can do with the difficult to isolate impurity. So for the easy to isolate impurities, we selected the enriched design as shown in this chromatogram here, with impurities in the front and in the back selected for accumulation. And here the result was the accumulation of weakly adsorbing impurities worked very well, and of strongly adsorbing impurities likewise. This is the chromatogram I showed earlier. You can see the nice growth in figure A, and then in the depletion phase B, you can see already the final chromatogram prior to getting out the main compound. And in figure C, you can see the elution phase where the main compound was removed in the prior depletion phase. So where the main compound was previously, there's now a gap, and we are just eluting the accumulated impurities. So you can imagine that with this kind of chromatogram, we can get concentration of the impurities than in batch chromatography previously. And here, these are analytical results for different impurities. They were not characterized further, but except for HPLC, but this already showed that many of them could be obtained with a very high purity, exceeding 80 and even 90%, and most of them were exceeding at least 70%. So for the second impurity, the critical impurity, we chose the design that's shown here. So we enriched the back part of the peak where we expected this critical impurity to be, and we ran the accumulation phase. And as you can see here, we could not observe any visible accumulation on the left-hand side over 8 cycles of operation, but nevertheless, we decided to fractionate the final elution of this chromatogram, and we could actually see that what we thought was a not working accumulation had turned out to be actually an accumulation that had worked very well. So the impurity actually displaced the main compound, as shown by the analytics, leading to a similar chromatogram from cycle to cycle, but just with increasing amount of impurity. And with this, now we could showed that we could increase this impurity, which was prior impossible to isolate, to 90% at 19% yield, and taken even the neighboring fractions here into account, we could improve the yield to 56% at a purity of 88% and recover a milligram amount of this critical impurity. So overall, this study showed that Enrich was very powerful in purifying the impurities, and looking at the figures of how much time was used for the purification compared to HPLC, we could see almost a factor of 100 reduction when using Enrich. So we went down from more than 1,000 hours to 16 hours using Enrich at comparably high purity. And as a comparison, also you see results from FPLC, which is regular preparative batch chromatography, where we could just reach a purity of 8%. So this is not really a competitive process. Moreover, you can see how much a solvent can be saved. So we went to a liter from 75. So a massive improvements through Enrich, and for a more detailed reading, we would recommend you to have a look at this open access publication. We did also a second case study for oligonucleotide impurities. Again, this is published. You have the link here as an open access paper. And we also did Enrich to purify impurities of the oligonucleotide from chemical synthesis in the front and in the back. And similarly, like in the first case, we used reverse phase chromatography and the Quanticom Cube system, then an acetonitrile based system, also with additives which are typical for oligonucleotide purification. And we could also achieve accumulation of the impurities, the side compounds in the front and in the back. Here now, in this case, we have more compounds in the front than in the back. And the final fractionation phase also showed that we could obtain, after analysis by HPLC, it showed that we could obtain many of the side compounds pure. Here on this slide, you can see the analytical chromatogram on the left side, and the overlay with individual analytical chromatograms of the fractions on the lower part on the left-hand side. And also this time we did a comparison of the purity for the individual impurities that could be obtained using Enrich technology, and you can see a much higher purity of the individual impurities produced by Enrich. And also the concentration was increased a lot when comparing Enrich to batch chromatography. Summarizing the time consumed for purifying these impurities, we were ending up with more than 2,000 hours with HPLC chromatography, and with around 200 hours for Enrich, so a factor of 10 improvement using Enrich. And the purity was 54% for selected impurities here. And with HPLC, the purity was not assessed due to the unfavorable processing time. Now for the next case study, which is showing the enrichment of monoclonal antibody charge variant isoforms, I'd like to hand it over to my colleague from YMC America, Jay Preston, to carry you through this study.
All right, thank you, Thomas. Thank you for all the information so far. And I'm going to continue with the similar format to the case studies that you've provided, talking about a monoclonal antibody purification of the isoforms that we did in our lab here in California. It was a sample that was presented where the company giving it to us wanted to isolate both the acidic and basic forms. The chromatography had already been developed for it, and we were just going to take that and convert it into a enrich process. They told us that they knew they had some isoforms at very low levels, and they'd like to accumulate and collect as many different isoforms as possible. So we used a Contachrome Cube 30 and the YMC BioPro SP material for the separation with a phosphate buffer and a phosphate buffered with sodium chloride as the strong solvent. So the first thing that we did was to generate a chromatogram, a single column batch chromatogram using their methodology in our lab on an analytical system. And the two chromatograms on the screen are the full scale version of it and the zoomed in version of it. And you can see, as typical in monoclonal antibody chromatography, there's a bunch of peaks rising up on the front and a few peaks on the back, not very well separated because they're all very similar. The next step is to transfer that analytical methodology onto the cube. So the methodology is directly compared from one to the other. And then this overlay shows the chromatogram from the analytical system superimposed on top of the cube chromatogram. And you can see the profile is very similar. Even though the cube is a prep system, it still gives you decent chromatography. The next step is to evaluate the loading by increasing the injection volumes. We start small where we could see everything we wanted to see, and we keep increasing until basically the front impurities are no longer visible. The orange trace on the overlay on the screen is way overloaded, and we can't see any of the isolation in the front. The blue one, we can still see a hint of the separation on the early eluting impurities. We then decide to use that level of loading for the methodology and set the parameters with the proper gradient and oval faces and columns. And then, as Thomas had highlighted out, the next step is to take it into the wizard. The first part of the wizard is to set the points of where the recycled is. The data from the single column batch is pulled directly into the wizard for this, and then you can just draw the lines, the blue lines, the red lines, and the green line of where you want to recycle the early part, remove the main peak part, and then recycle the late eluting part. And then the next step is to set the parameters, things like the max flow, feed, how to clean the columns, and how to re-equilibrate the columns. And then the wizard has a few more steps into it that sets the dynamic process control, which allows for the two columns to be slightly different. It's actually a very key element in the twin column processes. And then has a process prediction page and a solvent usage page. And then the next step is to run the accumulation step. So as you can see, the same data is presented twice. On the left is a linear with time, and you can see the peaks growing from the left to the right. And on the chromatogram overlay on the right side is the overlaid version of it, where you can see the accumulation of the materials going up and up, as similar to what Thomas had shown before. The red trace is the column 1 detector, and the blue trace is column 2. And I'd like to point out that this looks very similar to the data Thomas had shown earlier. Those were for peptides and also for oligos using reverse phase. This is for a monoclonal antibody using ion exchange. The technique works, as well with both kinds of methodology. This is a comparison of the very first injection on the top with the 10th injection on the bottom, and you can see all the material that is accumulated in the blue region and in the green region. And then the fractionation run is performed after the depletion step. The depletion step is a no-load injected version where you take out the main peak. That's why there's a big dip kind of in the center of that. That's where the main peak was. The change in gradient here was just a flattening of the gradient. the time that it was run was extended 2x. A lot of fractions are collected in order to isolate the different peaks. These were collected at 1 minute apiece. We could have used a different column in a completely different mode, but we felt that the separation and resolution was going to be sufficient with this type of system. And then these are analytical overlays of the resulting fractions, superimposed on top of the crude. So the blue traces the crude material, and then these are the fractions 3, 4, 5, and 6 overlaid. And you can see that we have found 5 different impurity peaks or related isoforms in the materials of these fractions. And then fractions 7, 8, 9, and 10 just move over, but we're finding the isoforms 6, 7, 8, 9, and 10 in under there. And then we go to where the main peak was, and we find isoform 11 and 12. And then in several peaks, we actually have a little bit of the main peak in it. And that's because we didn't try to cut out all of the main peak, because we were looking for the isoforms that were closely eluding on the edge or overlapping with the main peak. And then some of the late eluders are here. There's a little bit apparent in the bottom fraction. And then we have isoform 13, 14, 15, and 16. And then 17, 18, 19, 20, and 21 were also isolated here. So overall, we found 21 different isoforms. When the company gave it to us, they said they were expecting about 10 to 12. But when you start to do this in Rich, you start to pull things up that were poorly visible, if visible at all, under the regular concentration levels. Another interesting point was the isolation of isoforms that were underneath the main peak itself. You know, these were not visible under the analytical conditions that we had, and they would have been almost impossible to isolate without enrich. If you were trying to do just plain fractionation, these would have been buried under the main part of the parent peak, but by removing the parent and enriching these pieces, we were able to isolate components that might not have been achievable under typical prep chromatography conditions, single column. This is a summary of the process itself, going through the different steps and how long it really takes. The very first batch run was about 45 minutes. That's after it was already developed. So they gave us the method. We just had to run it on the cube. Then we took that cube data, put it into the wizard. That only really takes, you know, honestly, it takes about 10 minutes, but I always give about a buffer of 30 minutes when you're doing these kinds of estimates. The start method is the preloading of the column before the accumulation recycling steps go. Only takes 15 minutes. 5 cycles of an enrich method was 4 hours. A no-load run was 30 minutes, and then the fractionation run was 30 minutes, but for a total of about 7 hours. That does not include the analytical work at the end, but in 7 hours, we generated more material than this company had generated in a month by running their single column batch methodology. And it was a very successful project. When the company saw the results for this, they actually went out and they bought a cube the very next week, just because of the time savings and the amount of material they could accumulate. And with that, I will hand it back to Thomas for the key advantages of Enrich and to wrap things up.
Thanks, Jay, for showing this very impressive data from your work with the company on monoclonal antibodies. So wrapping up the advantages of Enrich, we can summarize that one of the key advantages that is that reduction of samples that we need to get to the target amount of our required site compounds. So instead of having to run dozens of injections, generating dozens of samples, we can only limit ourselves to one enrich run and have final fractionations with much fewer samples. So we can certainly reduce the number of samples by tenfold, and this advantage will increase, of course, with the number of injections. these analytics takes time. They take time, they are expensive. So avoiding them is certainly a great benefit. Also, we are generating samples of much higher concentration with enrich than with regular batch chromatography, where we have many diluted samples that need to undergo some kind of concentration step to get to a reasonable concentration. This could be UFDF, centrifugation, lyophilization. So these concentrated samples then go to the analytics, but the concentration step itself also can lead to product loss. So it's not only that is some additional handling, but also some product can get stuck, for example, in the centrifugal filter or during the UFDF due to some aggregation process. So in enrich, the concentration of this side compounds is intrinsic to the process. It's included. It's coming for free with the process. So we come out with high concentration. We save time also that could lead to degradation. So another great advantage of this process. Speaking of the manual handling, since we have fewer samples and we do not do up concentration, we do not require up concentration, we can save a lot of time also on the manual handling and use that time for other useful things. So with this, I'd like to wrap up the presentation. So I hope we could show to you that enrich is a technology very useful for automated preparation of side compounds and impurity standards that is running on a Quantichrom Cube benchtop chromatography system. It is reducing the processing time. It increases the purity of the standards, and also it reduces the number of analytical samples. So it's running fully automatic, and also it's a platform technology that works for various types of molecules, so peptides, oligos, antibodies, and possibly also other targets. Wherever gradient chromatography can be used to achieve some kind of separation of the compounds of interest, we can use enrich to generate those standards automatically. So with this, thanks for your attention. And we are open to taking some questions in our Q&A session.
All right, thank you very much for that informative presentation. Before we get started on the question and answer session, I would like to quickly remind our audience how to submit questions. You can submit your questions by typing them in the Q&A box, which can be found directly below the video player. I just want to confirm, do we have our speakers on? Hello.
Hello.
All right. I'm going to toss the first question out at you. What is the typical development time for setting up an enrich process for a new molecule?
So the setting up a enrich process is actually very straightforward once you have a batch chromatography methodology. So you would develop that under your normal conditions. And once you get to that point, in the third example we showed, I went over a quick timeline for something. It was only 7 hours to set it up and to run and accumulate material. Now that might be maybe a little faster than sometimes, but you could expect a full day to a couple of days for an enrich process after you have the batch chromatography all worked out.
Fantastic. Thank you very much. So our next question that came in, can this technology be scaled from lab scale to pilot or manufacturing scale?
Do you want that one, Thomas, or do you want me to take that one?
Yeah, I think, sorry, I'm back now. So yeah, the technology can be scaled also to pilot scale. The question is if you really want to do that. As for for pilot and manufacturing scale, typically you want to have consistent product produced over time from cycle to cycle. So you're not so much looking into producing impurity standards at a pilot or manufacturing scale, but you could do that in principle. So the equipment does allow for doing that.
Yeah. I'll chime in just a tiny bit on this one also. We have looked about using this for some natural product isolations where they were actually trying to pull the minor components out of bulk natural product material. And one of the interesting things on Enrich is you do not need to separate everything very well as you accumulate. So you can use a methodology that just separates out the components you don't want from the components you do want and accumulate them, and then run a good chromatography run in order to fractionate off of that. But the natural products are one area we have considered using Enrich technology for, maybe even commercial area.
Perfect. Thank you both. Another audience question that came in: how does the enrich process handle impurities that co-elute with the main product in a standard batch run?
All right. I can take this one too, Thomas. So if the material does not separate out, then enrich isn't really going to be that helpful, except for if it's on the edge of the main peak. Again, in that monoclonal antibody separation, we did isolate some material that were not separated from the main peak by consistently removing the bulk of the main peak and accumulating the edge. That material accumulated to the point that we were able to separate it out later on the fractionation step. So if the overlapping peak is on the front edge or back edge of the main peak, you might be able to accumulate it and isolate it further. If it's a broad, complete overlap, then as you remove the main peak, you're also going to be removing that impurity peak and won't accumulate.
Thank you very much.
I think we had one example of this in the presentation where actually there was a co-eluting impurity that was not exactly under the main peak, but already covered by the main peak, and that was successfully enriched also. That was batch chromatography. You would have not been able to purify that one at all, but with enrich it was possible.
Awesome, thank you. So you showed data for peptides, oligonucleotides, and monoclonal antibodies. Can that be applied to small molecules?
I'll take this one again, Thomas. Yes, it can be applied to small molecules. The one caveat is, as the material gets passed from one column to the other, because this is a twin column technology, there's an inline dilution that weakens the eluent so that the material will basically stick at the head of the second column. So when you add the more crude, it goes through as a nice tight plug. Sometimes small molecules don't dilute and stick very well on that second column. So you need to evaluate whether you can dilute the feed from the first column enough that it will concentrate at the head of the column on the second one for the next step of the run. That's the only caveat. If you can dilute the material and get it to concentrate on the head of the second column, then with a small molecule, then it's perfectly acceptable to run any of the twin column technologies.
Fantastic, thank you. So another audience question that came in, can the twin column be used for gradient elution impurities?
Yeah, so definitely it can be used. It was shown also in the presentation. So the process can run linear gradients, and again, the condition is that the eluate for the recycling has to be inline dilutable to reabsorb on the next column, and that is the case in gradient chromatography. So yes, definitely it can be used, and it's a great advantage because the gradient also sharpens the profile and increases the concentration of the impurities.
Great, thank you. So at a time, how many impurities can be impurities isolated and collected, especially if I'm looking for generic small molecule related impurities?
There's
So
really,
yeah, I mean, you want to
yeah,
take
go
that?
ahead, Thomas.
Okay. I was just going to say, I mean, the number of impurities that you can isolate and collect depends on the width of the recycling phase of the process, right? So you can drag those lines, as was shown in this wizard, to the front and in the back to have a very large region of the chromatogram to be accumulated, right, or to be grown. So it really depends on that. And again, for small molecules, you have this condition that you need to be able to reabsorb them during the inline dilution, as Jay explained, so that they stay inside the process and do not leave the second column also after the recycling. Yeah, so it can be very many. So we have shown in the examples that we have purified like 10 or even more, 15 impurities at the time, right? In the case of oligonucleotides and peptides.
Perfect, thank you. So the audience would also like to know, could the enriched technology also be applied to the isolation and purification of alkaloid compounds from complex plant extracts, given their structural diversity and the challenges associated with traditional chromatographic separation?
I would say it certainly could. Now, there's not a special magic to the enrich. If the chromatography doesn't separate things out, then enrich has a little bit of magic, as we just mentioned, about components that elute on the edge. But if the components are not separated from the others, then enrich isn't going to really help accumulate them. That being said, if they have a wide range and diverse material, you might separate them out in chunks. You may do all the very early eluters in one section, all the middle eluters in another, and late eluters in a third section, in order to concentrate them down and then put them on a second type of chromatography in order to separate them out. So it may be in stages. But I definitely say that if chromatography will work at all for the alkaloid compounds, then enrich will definitely be a use for the minor components.
Great, thank you very much. So then, aside from the overlap between the impurity and the sample mentioned before, what would be some other limitations for this method?
As I mentioned, for the small molecules, if you cannot dilute the material between the two columns in order to get it to concentrate on the head of the second column, then those compounds aren't good candidates for this technique. Other than that, pretty much any chromatography that you can do that type of separation on, and it's not limited to reverse phase, ion exchange works, HIC works. Any type of partitioning chromatography can be applied to this.
Perfect. Thank you very much. With that, it looks like it's already time to start wrapping up. So I want to start by thanking the audience for attending and participating in today's event. I'd also like to thank our sponsor, YMC, for making today's educational webcast possible. We had a lot of great questions. Any that we didn't get to today can be answered offline, but we would like to ask everyone in the audience to participate in a brief survey, and that's just going to appear when today's presentation has closed out. You're also going to receive an email alerting you when this webcast will be available for replay on demand, and we invite you to forward that announcement to any of your colleagues who may have missed today's live event. Otherwise, we hope to see everyone next time. Thank you, and take care.
Thank you.
Thank you.